Swayam Prabha. Digital India. Educated India.
Okay, welcome back. We'll change track a little bit. So we'll talk very different things. So what we had been discussing was the ways to remove carbon dioxide. We talked about ocean-based approaches, land-based approaches, and ocean-based approaches. Some of them with changing the acidity of the oceans by making them more alkaline, back to alkalinity, or in marine cultivation of algal matter and fertilizations. The part which is still being explored is also coastal blue carbon, which is changing coastal utilization. So along the coast, whatever we're doing with either mangrove growth or seagrass projects to change that part. So there are quite a few options that we have to fix carbon dioxide. I will not talk about capture processes. I think you'll deal much more with this, with post-combustion, pre-combustion systems to capture carbon dioxide, either after you have produced the power or the heat that you want with the flue gas that's coming out, or in front of the combustion system. So there are multiple lectures that will come at you through the process of doing that, and you will see enough examples of how to do that. What we will talk about is pretty much going from the capture side, what happens to the carbon dioxide once we have captured it, right? So we're looking at using these in this case out here to inject carbon dioxide into the subsurface, either to help recover oil or to fix it in place or to store it in place as carbon dioxide. So we are on this part here, and the reason this is that appealing is because we think that the storage security is guaranteed for tens of years, hundreds of years to centuries, multiple centuries. Ideally, it should not come out at all. And so that's why this becomes appealing on one case. On the other one is that it can have much higher capacity to store carbon dioxide. We're talking about tens of thousands of gigatons of carbon dioxide. So the capacity to store in the subsurface is enormous. Again, the part that is really interesting is if you look at all of the CCUS system. Now there is an added term that is needs to be tacked on, and that is the socio-technical part. And that is at the basis of everything. This is what we do in the technology, and here is where we interact with humans, with people living in places, with people making their homes in places. The public perception part is a big factor that has made or broken CCS projects all over the world. I'm sure you've heard of the term NIMBY. NIMBY, a concept? Not in my backyard. So that NIMBY means, and it was used as a term for many oil executives that were wanting to drill for oil and gas in other people's backyards, and they was living in nicely walled compounds with no oil and gas activity because they didn't want to live in a polluted place. And so the term NIMBY was coined there, and that moved very quickly into people saying, wait a minute, no, that works for me as well. So the NIMBY became a very common term. This has now changed into going from not in my backyard to being not in any backyard. And that's been what's troubling the carbon storage part quite a bit. And that's something we will discuss when we talk about a case study of the storage site that we are looking at. Okay, in all of this, if we are reusing carbon dioxide, I mean, there are capture technology, utilization, and storage in policy. This is something that we understand. This is something we're talking about. This is something we take for granted. And that's the part which is deals with resource limitation, public perception, and the actual impacts of storage. Okay, so let's take a quick refresher or a quick tutorial on what is storage, what is geologic storage. As far as I know, there are very few geoscientists. I think we have one person from NGRI, and most of you are not geoscientists. So we'll take a little bit of a refresher. These are potential worldwide storage targets. These are sedimentary basins all over the world. That's what makes it so appealing to every nation to say everyone has their own storage location. We don't need to go out somewhere. Some people, for example, here in Norway, in this part, they have made a big business case out of it, where they have created a storage capacity with loading docks for big container ships to come in, and they are selling storage space. They are sharing in the carbon credits so that that's their business model. They've created the storage space, they've built the loading docks, and now they are waiting for ships to come in and offload their carbon dioxide, the captured carbon dioxide, and store it in Norwegian project. It's called the Northern Lights. Very interesting to consider. That's a very big business model. It requires millions of dollars of investment, mostly done with government money, mostly done with money from the national, quasi-national oil company, Equinor in Norway. If you look at the color code here, these darker colors are highly potential, highly prospective sedimentary basins. These are proven up with their storage capacity. The lighter colors are prospective sedimentary basins, which means we're not so sure about it. The lightest shades out here, everywhere, these are the storage basins that are, or potential targets that are really, or sedimentary basins that are not targets. That can be for multiple reasons. There is not enough capacity. There is not enough seal. They're too shallow. There are too many fractures, or there are faults in the region, which means it makes it very prone to earthquakes. But if you look at every nation, there are enough storage basins that are present, that are proven. Highly prospective ones means everything is right for storage capacity, for seal integrity, for long-term storage. Out here, there is an active project from Chevron that has been active since a while. Out here in the North Sea, we have the Sleipner field, which is a saline aquifer that has been storing carbon dioxide for the past 30 years. Over here in Canada, in US, there are active projects that are currently being formed and injecting. So there is enough capacity. Here, the Insala project, which was a multinational was designed and investigated by about 5 or 6 different countries, different organizations, to characterize the field and do pilot injections. And so there are enough potential targets. So what do we really need? If we're looking at a storage site, these are potential injectors. This is a drilling rig that's used to drill a well down to wherever you want to be, and that is the injection site. For example, here we have injection in a saline aquifer. This is a schematic of the aquifer that might be present, that might be used for drinking water. This brown part is the seal. There is a fault here, and we are looking at how much this fault will interact with the injection here. The target formation is this yellow colored formation. If our storage formation comes close to the aquifer formation, then we need to rule this one out, because there is a high likelihood of that small amount of seal not being enough to prevent carbon dioxide from entering the aquifer. Over here, this seems to be a nice place, because here we have enough of seal rocks that will prevent carbon dioxide from migrating. And so if we look at potential escape mechanisms, let's say we've selected a site, we can go one by one. We have a site over here. We say that the capillary pressure, the pressure to enter small pores, is lower than the carbon dioxide pressure. If that happens, then carbon dioxide will enter into the seal formation and will migrate. So what we're trying to do is always keep that carbon dioxide pressure below the capillary pressure, so that it does not pass through here. Because this formation here is pinched out, the seal formation, that rock now allows carbon dioxide to go through, and before we know it, it's entering in the aquifer, and from there up into the siltstone. If we are out here at location B, we can see that the carbon dioxide is migrating here, and now it's going along this fault, escaping up. That's a much better conduit than diffusing through the silts. So this part is really not optimal. So we discard this one. If we go into C, as soon as I can locate it, right here, that's pretty much the same thing. It's going out here and through the cap here into the aquifer. If we are out in D, we have an up dip migration. We are injecting over here. Buoyancy will take carbon dioxide up dip, and so it will want to migrate up dip. And now we are at the we have to characterize this entire part, because we want to make sure that if it's going up here, there is nothing that will allow it to escape. If it goes this way, now we need to know what the permeability of that fault is, so that we have nothing that is escaping up dip. Okay? And so we can go through each one of these scenarios. If the formation is open to the surface, if it's all the way up here and it is exposed at the surface, then there is a very nice pathway for carbon dioxide to migrate up into low pressure regions. Now, there are ways to remediate. to say if this is happening, there are possibilities to overcome that. So in some cases, we can lower injection pressures to prevent migration or prevent migration very far. We can plug the well here, we can add new cement, we can drill it out and replace the cement. We can intercept and re-inject carbon dioxide over here. We can completely, I would abandon this site completely because there are too many problems out here. This is a cause for concern. If you are doing this, we usually do reservoir simulation models, and we will look at some of the reservoir simulation models where we create a scenario of injection here at a certain pressure and temperature, and against the background pressure and the buoyancy or the mobility of the injected fluid, we model how far it would go. We talked about that. Let me not go into that. I think we had discussed this a little bit, but we are at this place, if we are looking at geologic storage, all of these things need to happen so that we have enough supply of carbon dioxide to be coming to our disposal site. That's the model that the Norwegian Northern Lights is built on. It's like you design something, you design a container, now you wait for people to come in and fill the container so that you can get rid of it. So, carbon storage is an option, is a very viable option, is a mature option to get rid of carbon dioxide, and it's based on all of the knowledge that was gained for fossil fuels. So it's both a boon because we have knowledge, we are not learning from fresh. The technology levels are 7, 8, 9. It's a curse because people do not trust fossil fuel companies. Oil companies have a credibility problem, and so there is a challenge on needing the oil companies to do the storage, but not trusting them enough to do it properly or telling the public when they make a mistake. The part of that assumes that we are capturing carbon dioxide somewhere, right? You heard Dr. Saurabh talk about the carbon capture in either all of the flavors of hydrogen that you're creating or the other membranes or whatever you do, if you need to have net technology in place, the storage has to be part of it. And so we are able to guarantee at least 1,000, if not 10,000 gigatons of carbon storage capacity. These 1,000 gigatons of carbon storage capacity is larger than the storage requirements that will take us through 2100. And that's for the 1.5 degrees centigrade goal. If we go to 2 degrees centigrade goal, this timeline exceeds even further out. Now, there's one limiting factor, that's local geology and the storage capacity. But if we're talking on global scales, globally, that is available today. The technology is available today. The limiting factor is the capture amount. We don't have enough. The technology readiness levels are not high enough for us to be able to drill wells and wait for storage. Right now, what the best approach is to have storage wells right next to power plants, especially coal-fired power plants, and then examine how you will use the separations technology to be able to separate carbon dioxide in as pure a form as we can get. The challenge for permanent isolation is real, is there, but manageable and quantifiable. We have enough technologies in place that allow us to monitor and quantify how much carbon dioxide have we put in, come back in 20, 30 years and quantify the amounts that are still present and the location where they're present. This is not a new technology. This has been, the monitoring part has been shown for about 35, at least 35 years in Sleipner, where there has been constant, every 10 years, repeat measurements to be able to monitor and quantify. This is the amount of carbon dioxide that was put in. Here is how much we can account for it. And we know that it's not going anywhere else because we can image the carbon dioxide. And so all of this is present. And so the question that we really need to ask is, how are we going to do it? What are the systems, right? So let's look a little bit at the reservoir systems. And we know this from extracting fluids, extracting oil and gas. One of the critiques that we are putting to ourselves is to say, is fluid injection the same as fluid extraction? Is it? I see someone saying no, possibly not. Possibly there is one very fundamental difference, and that is the fluid extraction is non-reactive. There are fluids, oil and gas that we are extracting are non-reactive. What we are injecting is reactive. And so everything will change in that way. The second part is there is a lot of money to be made in fluid extraction. Fluid injection, there is no money to be made. The margins are very small. And so in fluid extraction, if you have a dry well, you declare it as a science well, collect as much information to make your next well pay for what you didn't find oil in. In this case, if we cannot inject where I drilled, my entire money is lost. That money, usually money is made after you drill and complete and prepare the well for storage, because you get carbon credits for storing. If you cannot store, then you've suddenly sunk about $20 million in drilling a well that is a science well, but you never intended your science well. So that's money, that's upfront investment that you have just lost. It's not recoverable. So this is not the same. The risks are much larger. Now, in the case of fluid extraction, you have an oil spill and you need to clean up, but you're making enough money that you can clean up. Fluid injection, carbon dioxide well. One of the biggest fears I have is every one of us needs to do something. You cannot afford for me to make a mistake in my project. I cannot afford for you to make a mistake in your project, because one mistake, one leak will kill all of the CCS projects all over the world. So the margin for error is very low in here as compared to here. The second part, or third, I don't know how many we've counted up already, one of the things is this here, if we are mapping in the fluid in the subsurface, we are mapping what nature has done. And the fluid calculations, fluid amount calculations in locations is constantly updated because of the production that we have. So we know how much must have been there based on what we are producing. And we can do decline curve analyses and so on to figure out, make the models better. In the case of injection, we don't have ground truth. We have to drill a well to get ground truth. And I just said, if we drill a well, we want to use it for injection, we cannot afford a science well, right? So this becomes a much more riskier target. In the project that I have, meaning we are a team of four different organizations. We are the lead on that. We have $33 million from the government to drill 2 wells. One of the wells we are at least 50% or if not more, 60% unsure whether we will have an injection site. And that's mainly because, one, the salinity might be too low, which means it would qualify as drinking water. Can't inject. The second one is the permeability is too high. We have drilled, our partners have drilled in the little bit north of where we are, and the permeability was in the order of 2 to 3 darcies. It was almost sand, which means the stiffness, mechanical integrity is not there. During drilling, the formation where they were going to inject was being produced, the formation itself. So they had to put in sand packers to make sure that they're not getting sand in the well bore. And so there are slight, it's a reverse process. You're not extracting, you're injecting, but there are challenges that come with it. So let's just take a quick refresher on oil and gas. Here are elements of a reservoir. You have a seal layer. The primary thing what you have are source rocks. These are organic rich rocks, shales you know them as. They go through high temperature, high pressure. They're buried, they're pressurized. The temperature increases. That leads to the organic matter maturing and yielding oil or gas, depending on the temperature, pressure, and the basic organic material. Now, that oil, let's just stay with oil, that oil migrates until it reaches a formation where it can accumulate, because that has enough capacity and it has enough of a seal to prevent it from going anywhere else. If you have different ways to trap it, there is a fault here that is sealing, there is a movement up here, so that here allows oil to pool in this zone here. If you have an anticline, that means your rocks are pushed together to give it a dome, your oil being less dense than the formation brine will migrate up here to collect in place. And now you can drill into here or drill into here and produce. So you need 3 things. 1, you need a source rock. 2nd, you need a storage formation. 3rd, you need a trap. Once you have all of these, you start getting a possible hydrocarbon reservoir. If whether it does become a reservoir or not, whether you produce it or not, depends on how much you have. Is it worthwhile? If you're a company like Shell or Exxon or BP, you will not drill into small little formations like this. You will sell this field off to a smaller company that has less overhead that will come in and drill it and still be profitable. So the part which you should remember is you need something that cooks with organic matter. That cooking gives you a maturation and generation of oil and gas. Then from that maturation, you need migration, where this is going up into a host. This is your host formation that allows things to accumulate, and this host becomes a good host if there is a trap in place. So that's your in a brief summary of what your reservoir looks like. And once you have that in place, you can look at a little bit more complex system, and that is your typical formation here. You are looking at your source rock here, and you have migration over here. This is your primary migration, and things are migrating up here or along here. You have a part where you can get gas and oil migrating. They separate out gravitatively, and so you have brine, oil, gas, density separation. Depending on which one you want to have, usually you will stay away from gas and you will produce your oil first. That's what's giving you the money. In today's world, no one wants to produce gas because it's not lucrative. I think India is one of the few markets where gas is still lucrative to produce. In many other places, gas is not lucrative. So for the US, for example, gas is being produced but mainly for export. If no one is there to buy it, it's not worth it. Okay, so where does the fluid reside? We have grains. These are solids. They don't contain any fluids. They're bound together by cement. So these jagged things are supposed to mark cements. And in between, we have these pore spaces. In this case, you have vugs, that is dissolved space. You have a fracture. All of these can contain fluids. That's where your fluids reside. Geologists love to give things names, and many complex names. So you have primary, secondary, intergranular, intragranular porosity. They dream this stuff up. I would not worry about it. I would look at pore space and say, there is pore space. We need enough of this pore space, both for oil for an oil reservoir to be productive and to be financially worthwhile. If we are designing a storage space, we need to have enough of this porosity present so that we can store in it. So that's the part that is simple. Now, it does become a little bit more complex because we have water wet and oil wet systems. So we need systems we have systems that have affinity for one fluid over the other. And depending on what fluid the rock has affinity to, distribution of fluids can be very different. So in this case, we have a water wet system, low water saturation, high water saturation. In low water saturation, the water coats mineral grains, and the oil in this case resides all around. It's easy to produce this one because water is not going to move, oil will move. And so this allows production even at low saturation of oil. At high water saturation, you still get that coat, but now your oil is in small blobs. This is not producible, it's not movable. If you start producing, the water will move because that has a connected space. Oil is not going to move. Now, if you have an oil wet system, when you have low water saturation, you can produce this one because oil is going to move. The water is not movable. You start getting more water saturation. Now you have a problem because oil is adhering to the surface of the grains. So when you start pulling on this, water will flow, oil will not. And so you have your immobile oil space that's not going to move. So now you need to use surfactants to promote the oil to move and the water to stick to these grains. So there are different methods. The part which we are interested in is what happens when you have carbon dioxide. You form a mild acid. Is it going to act as a surfactant and start dislodging things that were in, for example, an oil wet system? If you're looking at a depleted oil reservoir for storing, this becomes a big challenge because now you have oil that was immobile, but you've added carbon dioxide. Carbon dioxide, supercritical carbon dioxide, is a solvent, and we'll look at NMR data soon, where as soon as you put carbon dioxide in the system in supercritical state, even in liquid state, this one starts to move. Since you're not producing, it doesn't matter because it's not coming to your wellbore, but it does matter because if it's now starting to migrate, you don't only have to map your carbon dioxide, you also need to map this oil that you've started mobilizing. If you're looking at unconventional reservoirs, this is a very, very simple part to show, but there is very low permeability. So we drill a well. This is a well shown not to scale, but sort of proportional. This is here about 1,000 feet. Here's your typical aquifer zone. You have thousands of feet space that is occupied by various types of rocks, shales, non-shales, sandstones, usually containing some form of brine or the other. And then you reach a formation that has contains oil. In the case of unconventionals, your oil has not migrated very far. It is in place where it is cooked most of the times. And so instead of drilling a vertical well, you will have to drill a horizontal well and frack it in every location here. In this case, you have 11 fracking stages. That means you're putting in high pressure fluid here so that you create this complex fracture system, and that allows the fluid to come through and go into this drill string for production. Okay. So that's your petroleum reservoir system one-on-one. Now, we need pretty much the same technology, similar technology, but in reverse with caveats, which we named, for storage. So if we look at just the natural system, we have enough going back and forth from the land biosphere, from the oceans, up in the atmosphere, and that back again. So that's sort of the normal cycle that we have. We added, this is from Dressler 2016, we added about, let's say it's more or less the same, about 10 gigatons of carbon to the system. If we take geologic storage, according to Dressler, but he's not a geologist, there are millions and millions of gigaton of carbon storage space. Not necessarily true, but thousands of gigaton of carbon storage space, yes. So this is the one we are now trying to exploit. Where does this reside? We have depleted gas fields with about 690 gigatons of carbon capacity, depleted oil fields, carbon dioxide EOR fields with a capacity of 120 gigatons of carbon, and then we have deep saline aquifers where it can be tens of thousands of gigatons, and unminable coal seams. Unminable coal seams means they're too deep, you cannot really dig them out. It's not feasible to bring the coal to surface. So there is a process by which you can exchange out methane that's adsorbed onto the coal with carbon dioxide. And so what we're looking at here is the preferential affinity of one gas over the other. If you examine coals are fascinating. They have a very large surface area, they have a very high potential to store methane, and they do store methane, but that methane is held very tightly. It's adsorbed onto the surface. You need to reduce the partial pressure enough for the carbon dioxide to desorb, for the methane to desorb. That's not always feasible because now you have produced water from coal which you need to get rid of. And so what we use here is to say what is the preferential absorption of one gas over the other. Turns out that coal has maximum affinity for nitrogen, next highest for carbon dioxide, and further down for methane. So if you expose coal that has methane to carbon dioxide, the coal takes up the methane, takes up the carbon dioxide to release methane. So that's your coal bed methane recovery process with carbon dioxide. That is something, the supercritical carbon dioxide has a higher affinity with coal because of the access of carbon dioxide to the microporous regions. So the absorption is higher when you have supercritical carbon dioxide. There are very few studies on this, and so, but there are most of the work that has been done in the absorption process is on low pressure, not at high pressure that's needed to get this part clarified. But if you look at the mobility, the supercritical carbon dioxide has a much higher mobility. It's able to access the micropores much more. So that becomes much better to use for coal. Oftentimes, you don't have the choice whether you use liquid or supercritical carbon dioxide. That will be dictated by your thermal gradient and the pressure. So the pressure and temperature will dictate what phase your carbon dioxide will be in, and that's what you have to work with. So when we look at carbon dioxide, we are wanting to make sure that we have enough technology to do a proper MMV, monitor, measure, and verify. In some cases, MVA, monitor, verify, assess. And all of that technology is required to quantify and be able to prove that if I have put 10,000 tons of carbon dioxide in the surface, I can account for all 10,000 in wherever we think it will go. So we have a conceptual diagram here of various ways to store carbon dioxide. This is in the subsurface. We have saline aquifers here, and we have oil recovery out here. These can be depleted reservoirs, or it can be CO2 EOR, enhanced oil recovery. In this case, we are onshore and we have enhanced oil recovery. We have saline aquifers, and we have this, I think, is meant to depict methane, coal bed methane. So you have coal bed methane out here. We have saline aquifers that are onshore and offshore, and we have enhanced oil recovery both offshore and onshore. So these are some non-reactive storage options. These are options where the rock is the host rock. In this case, it is whatever the reservoir formation is for oil. In this case here, it's usually sandstones. Sandstones are non-reactive for the most part. And when we do geologic storage, we will examine this in more detail to say, are they really non-reactive, or is there more to the story? So if we are looking at geologic sequestration, we want to separate between storage and utilization. We can have utilization where we are using carbon dioxide to get more oil or more gas. We can use carbon dioxide to enhance coal bed methane. We can also use it for shale gas recovery. One of the things that we are exploring now, this is in collaboration with Iceland, is to drill wells to have geothermal systems, but not use steam or water as the heat exchange medium, but use carbon dioxide, which is much more efficient. They are excited about it because it's something they have not tried. We are excited because it's not a very expensive well to drill. The heat source is very near. And so the idea is to have an enhanced geothermal system that is either open loop or closed loop. Most probably we'll try with the closed loop. Geothermal systems are a concept here? No, okay. Okay, so what you do is, can I write with this over here? I need to change the pointer, right? Not that way? Okay. Okay, then I can write. So what you have is here, you have the surface. You have, this is your derrick here. This is another derrick, but you don't really need that. You have a well that goes in here and that comes out here. In a closed loop system, you are going through like this here. This is a closed loop system. You're injecting fluid here, cold fluid here, and you're producing hot fluid here, right? So that's your closed loop system. Now, if you don't want a closed loop system, so if you don't want a closed loop system, you take this one here and you bring it close here, but you don't tie it together. These are two separate systems, and so you're still injecting here, you're still producing here, but now you have a little bit more space out here for the reaction to take place. So you have a much more efficient way to get heat out, right? Because you have much more contact. So this is your hot rock here. So all of this is hot rock, and so your fluid is meant to be just occupying this space and go out here. And there are multiple variations of these, but these are two of the ones that would be considered. So if we can, right now, this is water that's used, and steam comes out this side. To make this thing more lucrative, you need about 140 degrees C temperature out here, right? The steam that comes out should be at 140 degrees C. That makes it worthwhile to have an energy system. Otherwise, you have low-grade geothermal systems. So you can have that part. Now, what we are looking at is to say, well,